How can messy molecules organize into nanostructures so precise they rival engineered materials? In the world of thermodynamics, entropy tends to win. Left to themselves, systems naturally evolve toward disorder. This is why gases spread, why ice melts, and why your neatly arranged desk inevitably becomes cluttered. So, here's the paradox. Block copolymers, long-chain molecules made of two or more chemically distinct segments, somehow spontaneously self-assemble into intricate, highly ordered nanostructures, and they do this not under strict control, but through free, entropy-governed motion in a warm solution or melt. How does this happen, and why doesn't entropy, normally the champion of disorder, tear these structures apart? Block copolymers are a type of soft material often made by linking two different polymer chains end to end, such as polystyrene, rigid, hydrophobic, and polyisoprene, flexible, rubbery. These two blocks are chemically incompatible. They don't like to mix. However, because they are covalently bonded, they cannot phase separate completely like oil and water. Instead, they find a compromise. They microphase separate into repeating nanoscale patterns, stripes, spheres, cylinders, gyroids, depending on the length, volume ratio, and interaction strength between the blocks. But why such order? The driving force lies in a delicate tug-of-war between enthalpy and entropy. The enthalpy, related to energy minimization, encourages segregation of unlike polymer blocks to reduce unfavorable interactions. Meanwhile, entropy resists this separation, especially because stretching polymer chains into regular patterns is entropically costly. The system resolves this by forming periodic nanoscale domains where each block occupies a separate region, but with just enough stretching to avoid full mixing or full segregation. This results in self-assembled structures with remarkable regularity, often at scales between 5 and 50 nanometers. What's fascinating is that these structures can mimic those seen in crystals, photonic materials, or biological membranes, even though the process is entirely bottom-up and thermally driven. No external mold or top-down lithography is needed. You might ask, if the system is full of random motion, how does such perfect patterning emerge? The key lies in the fact that block copolymers explore many configurations but settle into those that minimize the system's free energy. That is, the final pattern isn't imposed. It's selected from a vast statistical ensemble of possibilities. These self-assembled states represent a kind of order born from frustration. The polymers are trapped between the urge to separate and the obligation to stay connected. The result? A compromised structure that is locally ordered, globally repeatable, and tunable by adjusting molecular parameters. This paradox becomes even richer when block copolymers are confined, such as in thin films or within nanoscale templates. The competition between natural self-assembly and external constraints leads to novel morphologies, defect control, and pattern alignment. Turning a simple polymer melt into a nanoscale design toolkit, applications are plenty. Block copolymers are being used to make nanoscale templates for electronics, drug delivery vehicles, membranes for selective filtration, and even metamaterials with unusual optical or magnetic properties. Their ability to self-organize into complex, functional geometries makes them ideal candidates for next-generation nanofabrication, especially where traditional top-down methods reach their resolution limits. So what does this paradox teach us? That order doesn't always need strict control. Sometimes systems governed by simple physical principles, like incompatible molecules tethered together, can explore their way to complexity. Self-assembly isn't a failure of entropy. It's entropy finding a new kind of harmony with structure, and block polymers are a beautiful example of how chemistry, physics, and thermodynamics dance together to create function from form, and order from the seemingly chaotic world of soft matter. The block polymer self-assembly paradox arises from the surprising observation that chains of dissimilar polymers, covalently linked into one molecule, can spontaneously organize into highly ordered nanoscale patterns, including spheres, cylinders, gyroids, and lamellae. This seems paradoxical, because polymers in solution typically form disordered entropic coils. Yet in these systems without external guidance or templates, order emerges from disorder, forming periodic nanostructures with precision approaching that of crystalline solids. This challenges our understanding of entropy and self-organization in soft matter. A D-block copolymer composed of polystyrene and polymethyl methacrylate can phase separate into alternating lamellar domains of tilde-20 m thickness, forming periodic layers across microns of material. It is like tying spaghetti and linguine into a single noodle strand, tossing thousands of them into a pot, and watching them neatly separate into stripes with perfect spacing. Block copolymers are made of two or more chemically distinct polymer blocks covalently bonded into one molecule. These blocks tend to phase separate just like oil and water, but the covalent linkage prevents full demixing, forcing the system into a compromise. The result is microphase separation, where each block forms its own domain, but on a nanoscale, governed by thermodynamic balance. The paradox lies in how these molecules coordinate long-range patterns despite being governed by local entropic movements. Triblock copolymers, such as polystyrene polyisoprene, polystyrene, can form nanostructured thermoplastic elastomers, where hard and soft domains alternate, giving rise to useful mechanical properties. It's like being handcuffed to someone you dislike. You're forced to share space, but each person claims their corner of the room in a fixed pattern. The driving force for self-assembly is a delicate interplay between enthalpic repulsion and entropic constraints. The different blocks repel each other, creating surface tension between domains, while the polymer chains are constrained by their covalent bonds and conformational entropy. This competition leads to well-defined, energy-minimized structures that depend on the block volume fractions, interaction strength, and overall chain length. These systems reach equilibrium structures through self-organization, not external templates. Changing the volume ratio of two blocks from 50 to 70 to 30 transforms the morphology from lamellae to cylinders or spheres, enabling tunable nanostructure design. It's like a game of tug-of-war, where each side is connected by a rubber band. They cannot fully separate, so they arrange into loops, walls, or tubes that minimize strain. Block copolymers exemplify how simple, local rules, like immiscibility and chain connectivity, can generate complex, long-range order. This is a hallmark of emergent behavior in complex systems, where global patterns arise from competing interactions and energy minimization. These materials form spatially periodic structures without crystalline order or external direction, acting as self-programmed templates for nanoscale engineering. In directed self-assembly, block copolymers are guided by patterned surfaces to form integrated circuits at sub-10 m scales, bridging the gap between bottom-up and top-down fabrication. It's like pouring colored sand into a vibrating tray and watching it spontaneously sort itself into intricate, repeating mosaics, without anyone drawing the pattern. The self-assembly process is governed by the minimization of the free energy landscape, where the system navigates competing contributions from interfacial energy and entropy loss. Although entropy generally favors disorder, in block copolymers, the entropic penalty of stretching chains outweighs the disordering tendency, leading to an ordered phase that is entropically stabilized. These systems settle into metastable or global minima, depending on processing conditions like annealing, solvent exposure, or thermal gradients. Solvent vapor annealing allows block copolymers to rearrange into well-ordered domains by temporarily enhancing chain mobility, allowing the system to escape local minima. It's like shaking a snow globe until the flakes arrange into concentric rings, not random, but energetically favored by the way the flakes interact with water and each other. From an information theoretic view, block copolymers encode spatial information in their molecular architecture. The sequence, length, and chemistry of each block act as a molecular instruction set, determining the resulting nanostructure. This allows for bottom-up fabrication of complex geometries without lithography or scaffolding. The system self-assembles in a way that appears almost programmed, though no external blueprint is present. By designing block copolymers with added functional segments, researchers can program materials to form hierarchical structures with multiple length scales of order used in photonics or biosensors. It's like embedding architectural blueprints into Lego bricks. The blocks know how to assemble into walls, arches, or domes based purely on their shape and compatibility. The ability of block copolymers to self-assemble into tunable nanostructures has revolutionized fields ranging from drug delivery and nanolithography to photonic materials and filtration membranes. These materials can form uniform nanoscale pores, channels, or multi-layer coatings, often with minimal processing. In medicine, they serve as nanocarriers that disassemble in response to stimuli, while in electronics, they enable the patterning of semiconductor components beyond the limits of traditional photolithography. Block Copolymer thin films are used to template silicon etching in advanced semiconductor manufacturing, enabling the creation of self-folding paper to build miniature robots. The structure is already embedded in the material itself. Despite their self-organizing nature, block copolymers face challenges in kinetic trapping, domain alignment, and defect elimination. Reaching the equilibrium structure may require thermal or solvent annealing, and defects introduced during processing can compromise functionality. Aligning domains over large areas for practical applications requires surface patterning, shear fields, or electric guidance, bridging the gap between spontaneous assembly and engineered precision. Using graphoepitaxy or chemoepitaxy, block copolymer domains are aligned over large wafers by patterned substrate features, enabling integration with silicon chip fabrication. It's like nudging a crowd to stand in neat lines at a concert. Everyone wants personal space, but a little guidance ensures perfect formation. Block copolymer research is expanding toward multi-block systems, hierarchical assemblies, and responsive architectures. Combining self-assembly with external fields, AI-guided design, or genetic control may yield programmable matter that responds to light, pH, temperature, or biomolecular cues. The field also opens philosophical questions about how complex form emerges from simple connectivity, offering a model system to explore emergent order, encoded design, and soft material intelligence. Researchers are now developing block copolymers that respond dynamically to biological environments, forming adaptive membranes or artificial organelles. It's like building a city from smart bricks that know when and where to connect, repair, or reshape an ecosystem of form written into matter itself.